Right, in this video we're going to try and draw a Born-Haber cycle for sodium chloride. So the best place to start with Born-Haber cycles is we'll start at the bottom and we'll draw a line, preferably with a ruler for you guys. Right, and on that line we're going to draw the ionic substance, so in this case sodium chloride. Now, one of the things we need to do for Born-Haber cycles is make sure we include all the state symbols. So it's an ionic substance, it's going to be solid at room temperature. Right, first thing we're going to do is we're going to put in the lattice enthalpy of formation. So the lattice enthalpy of formation goes from our elements as gaseous ions. So that's going to be, sodium's in group 1, so that's going to be +1, and it's got to be a gas. And chlorine becomes chloride, it's going to be Cl-, and again, that's a gas. And then I need to draw this line down to the bottom, making sure the arrow goes the right way. And this is the lattice enthalpy of formation. Remember, there's a lattice enthalpy of dissociation as well. So if it was a lattice enthalpy of dissociation, it would be going from the NaCl as a solid to the gaseous ions. So the lattice enthalpy of formation of sodium chloride is that. Now, this is like a big Haber cycle that we did last year, except it's more complicated. So we're going from the gaseous ions to the ionic solid here. We need to go the other way around. So we need to find different enthalpies that can go from sodium chloride as a solid to the gaseous ions, but we need to go around in the other direction. So the other enthalpy change that we looked at last lesson, which involved the compound, is the enthalpy of formation. So the enthalpy of formation, as we know, goes from our elements in their standard state. So sodium is a metal, so at room temperature it's going to be a solid. So that's going to be Na and an S. And then chlorine, because it's a halogen, is always going to come as it's diatomic, so it's going to be Cl2. And hopefully we know that chlorine is a gas. Now, because I've only got one chlorine atom in my, one chlorine, it's going to be an ion, isn't it? Not an atom, because it's Na plus Cl-. But because there's only one chlorine in NaCl, I need to have a half here. And it's these little details that people forget when they're drawing these cycles. So I've now got my sodium solid, which needs to turn into the the gaseous ion, and I've got my half of my chlorine molecule, which needs to turn into my chloride ion, that's a gas. Now, it doesn't matter which one of these you take first, but the last step is going down to here is the electron affinity, and that's for the chlorine. So it makes sense in my mind to do the metal first. So we're going to do sodium first. So the first step is I need to take the sodium as a solid and I need to turn it into a gas. And this is called the, I've not labeled this. This should be the enthalpy of formation. So that's the enthalpy of formation of sodium chloride. Right, and then here I need to put, we need to make sure the arrows are going in the right direction. So it's going from the sodium as a solid to the sodium as a gas. And then I've got to include my half Cl2, exactly the same as it was before. So that's going to be the enthalpy of atomization of sodium. So if I look at this, I've got my sodium atom as a gas, and I need to turn it into a sodium ion as a gas, so it's got to lose an electron, and that's the first ionization energy. So my next step here is the first ionization energy. Of sodium. And that's going to turn it into Na plus gas. Now the bit I always forget, and we need to make sure we put in, is that I've generated Na plus ion. I've also got an electron. So I need to remember to put this electron in. And then I've still got my half Cl2. And again, I need to put the state symbol in for that. So if we look at this, the Na plus as a gas is exactly where it needs to be. So all I need to do now is turn the half Cl2 as a gas into Cl minus as a gas. So the first thing I need to do, let's just move this paper down, is I need to do atomization. So we've already done atomization of sodium. I need to now do atomization of chlorine. Okay, and I'm going to draw that line further along now because it's the furthest to the top that we need to do. And that's going to give me, so my Na plus as a gas and my electrons stay the same. But this half Cl2 is going to turn into a gaseous chlorine atom. Okay, so we're nearly there. I need to label that. So that's my enthalpy of atomization of my chlorine. And then my last one is Cl as a gaseous atom being turned into a chloride, gaseous chloride ion. And I'm going to put the arrow going down there. This is my electron affinity. So that's my electron affinity of chlorine. Okay, so now, I'm not sure if we can get that all in on one. Okay, so that's the completed Born-Haber cycle for sodium chloride. If we look at these, we'll see that the arrows going down are exothermic. So if I just write this at the top. So in a Born-Haber cycle, so arrows going down are exothermic. Arrows going up are endothermic. So you can see here electron affinities. The first electron affinity is always exothermic because you're forming a bond between the electron and the positive nucleus. When we do have one, so when you do one involving something like oxygen that gains 2 electrons, so the second electron affinity is negative because then you're trying to add something that's negative. So you're trying to add a negative electron to something that's already negative, and that causes a repulsion. So let's just make a note here that the first electron affinity is exothermic. The second electron affinity is endothermic. Okay, so most Born-Haber cycles are going to look something like that. Where there's a difference, so possible differences so if I had something like Na2O, then I'm going to have 2 of the sodium ions in there, so I need to include that in my cycle. And here I'm going to have first and second electron affinity. And because of that, what the top of this Born-Haber cycle is going to look like this. So I'm going to have, so that's my atomization. Then I'll have the first electron affinity there. And then I'll have, so the first electron affinity is exothermic, the second electron affinity is endothermic, so the arrow's got to go up. So you have a second one there. And then this would be my gaseous ion. So in this case, it would be 2Na plus as a gas plus O2 minus as a gas. And then that would go down all the way to the bottom to the sodium oxide. So if you have a 2 minus ion, you're going to end up with something like that. Other differences you might have to watch out for. So, for example, I had something like barium chloride, then I'm going to have 2Cl minus. So I need to take that into account. So my atomization is going to be times by 2, and my electron affinity is going to be times by 2. And for the barium there, because that's barium 2 plus, I'm going to have first and second ionization energies. Right, I hope that hasn't ended up as too much of a scribble mess. I will scan this sheet in and email it to you. What I want you to do now is practice your own Born-Haber cycle. So I want you to have a go at drawing the magnesium chloride Born-Haber cycle. So that starts you off. When you've finished it, I want you to check in the textbook. It's got the final one, so check that you've got everything correct in the textbook. Okay, thank you for listening. See you next time.